In the name of God, hi, my name is Mohammad Mahdi Mohsen. In this project, I'm going to talk about this bidirectional DC-DC converter in this picture. This converter is a three-phase interleaved DC-DC converter which can convert 24 volts from its input port to 48 volts on its output port and vice versa. If I want to explain this converter, first of all, I have to say that I collaborated with one of our students in our laboratory, and I cannot show its topology of circuit because we are working on its paper to submit it, and I cannot reveal the circuit. And about my task in this project, I have to say that my task was to design its PCB and design its controller for step up or step down. It's better to say that for boost mode or buck mode of this converter, and implement this converter, you can see in this picture, and perform practical tests on this converter. First of all, I'm going to show its Altium, its PCB, an Altium Designer software. This is, you can see it has 4 switches and 2 inductors, and this converter, these switches of this converter turn on under ZVS condition because of two active clamp circuits that are integrated into this converter. Now, I'm going now to show, its simulation and this digital PI controller that I designed it. I cannot show its circuit again, I have to say that, because we are working on its paper. We have phase 1, phase 2, phase 3, which are connected in parallel connection, as you can see. And this converter, the first block, contains 4 switches, the second block again contains 4 switches, and the third block contains 4 switches too. And we have 2 main switches in each phase, in each part of this converter. For example, in boost mode, one of them is the main one, and in buck mode, the other one is the main one. And we have 2 active clamp switches to prepare ZVS condition for our semiconductors in this converter. Now, because we have 3 stages here, and the phase shift between these stages should be 120 degree because we have 3 stages, and if we want to find the phase shift degree between these stages, we have to set at 360 on the number of stages. So we have 3 stages, and the phase shift between the main switches and these 3 phases should be 120 degree. Now, as you can see, we have input DC supply and the output, and this is the compensator. This converter is going to work in boost mode. The input voltage is the input voltage is 24 initial output of this step, and the final output is 26. So the input voltage is going to be changed in the middle of simulation, and the output is going to change again. It's going to be changed by this switch. So the output power is going to be doubled when this switch is going to be turned on. And we have a PI digital controller. Our voltage reference is 48, and again you can see. Now I'm going to start the simulation. So this is the output voltage. As you can see, this converter stabilized stabilized 48 volts on its output port, okay, from here. And when the output load is changed, this converter again could stabilize its output port on 48 volts. And when the input voltage changes, after some time, the converter, we can see 48. The converter stabilized its output port on 48 volts. Now, I'm going to close this. This is the boost mode, and this is the buck mode, buck 3-phase. Again, we have that 3-phase, and because we have main switch and active clamp switch, so their pulses should be complementary, and the pulses should have a dead time. So again, I use this dead time generator for this converter, you can see. And I have, if I want to start the simulation, wait a minute, now we can see. Okay, two complementary signals with dead time. And now let me close this and going to this. Okay, the input voltage from 48 changes to 50, and the output power is going to be doubled again, and the voltage reference should be 24 volts. So we have 3-phase here, and I'm going to start the simulation. As you can see, this controller is helpful for this converter because the output voltage is stabilized or is regulated on 24 volts on this converter's output port. Again, the output power has changed, it's clear. So the converter regulated the output port voltage on 24 volts, and after the changes in input voltage, again the converter regulated the output port's voltage on 24 volts. Now you can see the PI controller, these parameters, and we have these parameters here. Okay, this compensator is designed for this converter to work in buck and boost mode with same parameters. Instead of changing these parameters in each mode, we designed this PI controller to work with same parameters in both buck mode and boost mode at 3-phase. Now I'm going to show a practical video of this converter. It's in English, and after that, after seeing this video, I will talk about that and say something about this. As you can see in this converter, we have 3-phase interleaf step-down converter, which it can work as a step-out tube. Look at here, we have 48.3 volts and 1 amps. It means that this source gives us approximately 49 watts. So we have here 24.37 volts on our output, which is work properly. In this oscilloscope that you can see, these pulses are given to our converter with the system 32. Look at here, system 32. It's controlling our converter. This is the drain source of the first stage, the first phase of this converter. As you can see, if I zoom it, as you can see, the voltage of drain source goes 0, and then after that we give pulse to our switch. It means that this switch is turning on the ZVS condition, as you can see. Here we have the inductor current, which is very clear. As you can see, It's completely equal to our simulation in PSPice, and that's it. Okay, now I'm going to talk about this video. As you can see in this video, I added many wires here to clamp or to measure current from each switch, the first stage, and inductors current. For each stage, I used two wires for this stage one for the main inductor, the other one for resonant inductor, and each stage. But only for stage 1 I use these wires to measure switches current, not for stage 2 and stage 3. The stage 2 and stage 3 only their inductors current are measured. And now, if you can see here, as you can see in step down converter, which it can work as a step up too. Look at your. Now, we have a circuit here. It's not clear, I think. We have a circuit here. It's here. This is a circuit which provides supply voltage for these gate drivers. These gate driver circuits. One power supply is connected to this voltage regulator circuit, and this voltage regulator circuit provides all power supplies. So it's an auxiliary circuit that I designed for this converter. Instead of using about 9 power supply, I only use 1 power supply, and I can have 9 output voltage for these gate driver circuits. Now about so approximately we have here 24 volts on this is the output load. You can see they are connected in parallel because we want to reduce their value to work properly. And this also here I have to say that you can see but this is 30. Look at here, it's 32. It's controlling our converter. This is the drain source of the first stage, the first phase of this converter. As you can see, if I zoom it, as you can see, the voltage of the drain source goes 0, and then after that we give pulse to our switch. Okay, now you can see that here. This is only because this oscilloscope has 4 channels. I can show the drain source voltage of the first switch in first phase, and all main switches and all switches, all semiconductors, turn on under ZVS condition. Which means that and another important tip about this is this. Wait a minute. Okay, I'm sorry. Now you can see this is the current of resonant inductor. I'm going to show its PSPice simulation. It's here. This is the PSPice simulation. This is the PSPice simulation result of this inductor. You can see they are equal. They are similar, not equal. They are similar. And another thing that I'm going to speak about that is this. This is result of boost mode of that converter. Only I measured inductor's current, main inductor's current, and you can see this this picture is for phase 1. This one is for phase 2. You can see these signals, these main switches signals, and the current of first inductor in first stage, the first phase, and the current of first inductor in the second stage. You can see in the 3-phase interlift, and I talked about all of them. Now I'm going to tell you that in this project the implementation, PCB design, and controlling on simulation, and other things. For example, practical tests were done by me, and I did all of them. And that's it. I hope you enjoyed that.